In this video, we're going to go over the basics of holomorphic functions, but first we're going to have to review some basics from real analysis about open sets, continuity, and so forth. First, it helps to pin down some notations for disks in the plane. The disk of radius r with center z will be written this way. This is the open disk, I should say, so it's all w's such that z minus w is strictly less than r. The closed disk of radius r centered at z will be written with a bar on top, and this is just the non-strict inequality holds. And then the circle of radius r centered at z will be written as the boundary of this disk. So it's all points w satisfying z minus w has modulus equal to r. Now the functions we typically consider will be defined on open sets, so let's quickly review open sets and domains and so forth. So a subset of the plane U is open if for every point in U there exists a disk centered at Z fully contained in U. So that's the standard definition of being open in the plane. Just means around every point you can put a disk around it that stays in the set. So it means you're far away from the boundary in a certain sense. And we also will be using sets called domains, and this is maybe poor terminology, but it makes a little sense because holomorphic functions that we'll be studying usually have their functional domain as what we're calling a domain here. So an open set will be called a domain if it's connected. And so for us, that'll just mean if you can write the set as a disjoint union, here's my notation for disjoint union. If you can write it as a disjoint union of two open sets, then one of these sets has to be empty. We do allow for open sets to be empty, just that's the standard practice in topology. Next, let's introduce some notation that's really helpful for talking about continuity and differentiability. It's very helpful to use this big O notation, which sometimes you see maybe when studying how sequences grow, but we'll use it with functions here. So here f and g will just be some functions defined near a point z naught. And we say f of z is big O of g. And so this is a whole sentence, f is big O of g. And that as z goes to z naught, and that just means that near z naught, so there exists an r such that for all z's within r of z naught, that f is bounded by a constant times g. So big O here just means f is controlled by g up to a constant. Now little o basically means that you can take the constant up here to be as small as you like, but you do have to pay the price of maybe you have to make the radius smaller. So we say f is little o of g as z goes to z naught means that for every epsilon, and epsilon is going to be our constant in front of g, we can attain that constant. For every epsilon, there exists a radius, so it would depend on epsilon, such that f is less than or equal to epsilon times g for all z in this small disk around z naught. And this means that f is much smaller than g near z naught. Now we'll use little o notation to efficiently describe continuity and complex differentiability. Okay, let's review continuity in the plane. So let f be a function defined on an open set U, and we say f is continuous at a point z0 inside of U if f of z minus f of z0 is little o of 1. It seems a little silly to use little o of 1, but it just means that the usual definition of continuity that you might be familiar with. So for every epsilon, there exists a delta such that for z minus z naught less than delta, which we previously wrote as z belonging to a disk, that whenever we have this, we have f of z minus f of z naught less than or equal to epsilon. So this is the usual epsilon delta definition of continuity, but it's efficiently captured with the little o notation. And now f is continuous on all of U if it is continuous at every point of U. Now let's look at complex differentiability. So again, let U be an open set in the plane, and let f be a function defined on U, and we say f is complex differentiable at a point z0 inside of U if f has this linear approximation property near z0, which means there exists a b in the complex numbers such that this difference, f of z minus f of z0 minus this linear term, is much smaller than a linear term in some sense. So it has to be little o of z minus z0 as z goes to z0. So this is the same as the usual difference quotient definition of derivatives, but again, little o makes it so you don't have to worry about what's happening exactly at z0, for instance. But here, let's write this out in the full quantifiers. So for every epsilon, there exists a delta such that for z close to z0, we have this bound, and if you divide through by z minus z0, which you can do when z is not equal to z0, you basically get the same difference quotient definition of a derivative that this quantity is tending to be as z goes to z0. Now, what is this b? Well, b here is uniquely determined, since if I had two different possible values for b, I could subtract two sides of this equation, and so let's say I had a b and a b prime that satisfied the same equation as here, I would get b minus b prime times z minus z0 is little o of z minus z0. So that's what I'm calling c up above here. And to have a constant times z minus z0 to be little o of z minus z0, that's only possible if c is 0, because I can't bound c times z minus z naught by epsilon times z minus z naught unless c is less than epsilon for all epsilon. So since b is unique, we can declare that the complex derivative of f at z naught to be this constant. Eventually we'll talk about how complex differentiability compares to usual notions of differentiability, but first let me just point out the even more basic fact that complex differentiability implies continuity at a point. The reason is complex differentiability tells us f of z minus f of z naught minus this linear term is little o of z minus z naught. Okay, but this part here is big O of z minus z naught, so you get that f of z minus z naught, f of z minus f of z naught is big O of z minus z naught. And this in turn is little o of 1 because you can make this arbitrarily small as z goes to z naught. Next, let's define holomorphic functions.